Have you ever figured something out and you tried to explain it to someone else and they just didn't believe you? This is the story about a man named Eugene Parker who in 1958 wrote a paper about solar winds.
NASA has named about 20 spacecraft after distinguished researchers. However, NASA has never named a spacecraft after a researcher during their lifetime. It is my great honor, a few days before your 90th birthday, Gene, to announce that we're renaming the Solar Probe Plus spacecraft to be known from now on as the Parker Solar Probe. Congratulations.
I wrote my speech down here. I'm certainly greatly honored to be associated with such a heroic scientific space mission. By heroic, of course, I'm referring to the temperature, the thermal radiation from the sun.
Every human that has ever lived has looked at the sun and thought about it. And this is mankind's best effort to understand it. It is time for us to go to Kennedy and ask hard questions. Okay, we made it. So there is a NASA press site over here. We're gonna go in there and see if we can find a scientist. So this is the press building, and all these different stations are set up with people that are involved in the launch and the science, and we get to just go walk up and ask questions. It's pretty cool. We'll just do it right here. I mean, it's super, super informal.
Excellent.
Destin and Angela,
Hi,
you
nice
work
to meet
with Mr. Parker?
So I'm the Physical Sciences Division Dean at the University of Chicago. So now I'm sort of responsible for all the physical sciences in Chicago. But my history in the 90s was a researcher, much junior than Gene, and now I'm a senior researcher, and he is now happy to be watching a launch of the probe, the Parker Solar Probe, that
So this
was
is
named
like
after him.
His life's work, right?
It's his life's work. He's incredibly humble and just loves physics. He loves astrophysics and loves to understand the universe by sitting down, writing equations, trying to understand how the physics in the cosmos works. The stuff we know on Earth, how does it get translated out there? And he would do that from an early age, and then when he came to the University of Chicago, he was very puzzled by what was going on with, for example, comet tails and other issues with the solar system as a whole, and sat down and wrote the equations that we call hydrodynamic equations for what would look like this plasma from the sun all the way to the edge of the solar system. And what he found was that there would be this solar wind, and he had a very hard time publishing that paper because people didn't believe it. People thought, no way, there is no wind, supersonic speeds coming from the sun all the way to the earth. There's nothing between the sun and the earth. It's really, just empty space, and there shouldn't be any problem flying out there, for example. Turns out he was right, and those who were very skeptical about him.
What made him see it? Like, what made him think it was there?
It was physics, so people had the equations that explained the universe, right? So people would make models and they assume there was nothing. So if you assume there's nothing between the sun and the earth, then, your solution will tell you zero. But if you look a little deeper and you say, well, wait a minute, could there be something? He would, which is what he did, and he found, yes, there is this whole solar wind, and nobody believed him. So he had a hard time publishing. This is 1958. By 1962, he got a bit lucky compared to many theorists because his theory was proved 4 years later. And that's what Mariner 2 did very precisely on its way to Venus and made it very clear that that's the solar wind. The Parker Solar Probe really was decades of work by many, many scientists. Getting close to the sun is no piece of cake, right? So the sun is very hot, the corona is even hotter. So it's an amazing design. The most impressive technological jump was the solar, the shield.
Before we go talk to the people that actually built the Parker Solar Probe, my daughter and I thought it'd be really fun to make a model version for ourselves. So we went to the craft room and made some awesomeness.
Be jealous.
Be jealous. This is awesome.
Be jealous.
So after talking to Angela, I kind of think of the spacecraft now like a shield on a Roman soldier, right? The enemy is the solar radiation, and no matter where the spacecraft is, it is always pointing that shield towards the sun to protect it from the enemy, which is, the thermal loading that would kill this thing in 10 seconds, as a matter of fact. Anyway, there's two things that had to be developed in order for this mission to happen. The first one are these high temperature solar panels, and the second one is the shield itself. So to learn about that, let's go talk to the Johns Hopkins Applied Physics Lab. This is Felipe from Johns Hopkins, right?
Yep, Johns Hopkins.
Over mechanical?
Deputy Lead Mechanical for the Parker Solar Probe.
So this is a big day for you, right?
This is a day that for me has been 4 years in the making. For most of the team at Johns Hopkins, 10 years in the making.
Really?
And for the space community, for NASA, this was a mission that was proposed in 1958.
Really?
So there's people that have been waiting for this for 60 years.
So you got on right at the tail
And
end.
got right on.
That's what I'm talking about.
I think the timing was perfect.
Do you call it the sun shield or the heat shield?
So
What do
we
you
call it the thermal protection system, the
Okay.
TPS.
Yeah.
And it's really what's letting us fly this mission. It's the reason why we haven't flown it in 60 years, because we hadn't come up with the right materials to do it. So the shield is a carbon-carbon foam sandwiched between two carbon-carbon reinforced panels. When we're close to the sun, where we're in our last 3 orbits of the close approach, the top of the shield will see 1300 degrees Celsius. It's about 11 centimeters thick, and when you get to the bottom, you're at 300 degrees Celsius.
So do you have radiators?
So we do, but the radiators are for the solar arrays. One of the really interesting challenges in this was figuring out how to power the spacecraft. Because we are going close to the sun, right? And so you have all of the solar flux you could ever want in the world. But the moment
you could melt them.
Right, so the moment you get an array out there, it's gone. And that's another of the key enabling things we've done is these arrays, instead of being built on like a honeycomb panel, like usual satellite arrays are, we've built them on a titanium platen that has microchannels flowing through it. And it's not fancy cool, it's just ionized water from a tank about this big inside the spacecraft that circulates here through the arrays, comes up to these 2 conical surfaces, and those are our radiators. And so that takes all the heat from the arrays and kicks it out to deep space.
So the sun shield is hyper important. So here's a question I have. If we are 8 light minutes away from Earth and anything that gets exposed in the back here to direct sunlight gets killed instantly, how do we keep this thing pointing? Because you can't get a signal there and back quick enough. And the answer is fascinating. On the back of the spacecraft, there are these little light sensors. And if you think about it, as you're pointing up there, as you start to tilt off axis and start to expose things, those little light sensors get exposed first. You see that way up there, right? Well, when that happens, the reaction wheels on the spacecraft itself, they use those to realign to make sure that they're pointed directly at the sun, which is fascinating. I think that's a really neat design feature. Next thing, this is called a Faraday cup. Let's see if we can figure out how that works. I'm Dustin.
Tony Case.
And who are you with?
I'm with the Smithsonian Astrophysical Observatory. So we're part of the Smithsonian, which is a lot of museums and a lot of research centers. And the Smithsonian Astrophysical Observatory is affiliated with Harvard, up at the Harvard Smithsonian Center for Astrophysics in Cambridge, Mass.
And so this is the instrument that's poking out from behind the thermal protection system.
This is it. So this is a qualification model. We used it to test before we built the actual version that's on the spacecraft.
So it's a one-to-one copy.
But this is a one-to-one copy, exact size, exact same materials and everything.
So what's the mesh right here?
So that's a fine tungsten grid, 90% transparent, and the particles flow through that.
And it's tungsten because it has the highest melting point.
Yep. And it's the hottest portion of the instrument. Right at the center of that grid gets up to 3,000 degrees Fahrenheit. And then behind the grid you can see in the front is another grid that we put at 6,000 volts. That creates an electric field. The charged particles then get reflected out because of that electric field, or they make it through if they have a high enough speed.
And then you're detecting those?
And then we detect them. In the very back there's a piece of metal that you won't be able to see here, but these 4 wires connect to that piece of metal. And so as the charged particles impact the metal, they deposit their charge, and we measure that as a current that's coming out through those wires.
So on these wires right here?
Yeah, so this is high voltage going up that drives the high voltage grid, and then the wires inside here are carrying the signal coming back out.
So you're driving the high voltage grid to guide what's coming in?
Yep, we can select the speed of particles that we want to measure by putting a certain voltage on the grid.
So is your wire made out of copper?
It's made out of niobium.
What?
Niobium. Yeah, copper would melt. It's way too hot for copper.
Okay.
So it's made out of niobium.
So how do you insulate something like that?
So it's insulated by little sapphire beads. So it's niobium on the outside here, and then sapphire beads.
What?
And then the niobium wire runs through each of those little bits of sapphire and through these little corners where there's little elbows made of sapphire. And in that way, the center conductor is insulated from the outer conductor.
So this is like, so basically you got a bunch of unobtainium and fantastilloid and you put them together and made a CRT tube that's way more fancy than that.
Yeah, no, I mean, think of it as like a vacuum tube. That's basically what it is. and it operates in vacuum, so you don't have to enclose it in glass. And so that's pretty much what it is. And you can select the speed of particles that are coming in with a voltage, and regulate the current that you end up with on your collector plate. So.
And the ultimate goal of this device, which is one of the main pieces of science on the spacecraft, is to count neutrinos. What is that the word?
Nope.
I'm an idiot. I am a mechanical engineer. I understand wrenches.
So this is, think of it as like what the sun is made of. Okay, there are a lot of neutrinos coming from the sun, but it's made of mostly hydrogen and helium. Okay. Those are the bulk constituents of the universe and of the sun. And so the hydrogen comes out as ionized hydrogen, or just protons, and the helium comes out as typically doubly ionized helium. So typically it would have 2 electrons. Both of those are stripped off. We call those alpha particles if you're talking about radiation. And those are the 2 main constituents of the solar wind, along with electrons. And we measure all of those.
So you're measuring flux.
Yes.
So you're measuring, like, as you get closer and closer to the sun, you're going to be able to understand the density of solar wind, not coronal mass ejections, because I'm assuming that would kill you if that happened.
Nope, we'll measure those.
Bull.
Yep. So.
Bull, you're not going to be able to, you're going to take a coronal mass ejection to the face.
Right to the face.
There's no way.
So,
really?
Yeah. So the cool thing about coronal mass ejections is it's basically the same plasma that is there all the time. It's just ejected in slightly more dense form and faster.
What are you talking about? I can see it. What are you saying?
You can see the solar wind too.
Okay.
In a coronal mass ejection.
Parker Solar Probe, fastest man-made object ever, decades worth of science, engineering miracles all over the place. When you dig into the hardware, this is a fascinating mission. I love it. The thing that makes this the fastest man-made object in history is the Delta IV Heavy. And the next video is me walking up to the Delta IV Heavy pad with Tory Bruno, the CEO of the company that made it, ULA, and just talking to him about the rocket. It is fascinating. I mean, like, you talk about access, like, it's on the pad. It's insane. Please check that video out. It's amazing. If you want to see the rest of these interviews, like in their entirety, that's over on the second channel. And this next thing you're about to watch is after we'd stayed up for 24 hours after launch. We've been driving for many hours, and we've been up for 24 hours. How's that feel, Trent?
I'm tired.
We're almost home. Here's the deal. I want to say thank you to the sponsor for this video, which is Audible. When we're on road trips, a good way to stay awake and a good way to engage your brain is getting audiobooks. Right now we're listening to How to Think, a Survival Guide for a World at Odds by Alan Jacobs. There's going to be differing opinions in this comment section because it's a YouTube video, right? So this book is really, really good to get rid of your cognitive biases. It helps you think about the other side's opinion and how you process that. It tells you a whole lot about yourself. So you can get this audiobook by going to audible.com/smarter, get a 30-day trial, first book's free, or text the word SMARTER to 500-500. Again, that's audible.com/smarter, or text the word SMARTER to 500-500. That's a big deal. It helps Smarter every day. It helps me pay for things like Trent, your thing. So that would be a big help. Also, this experience was amazing, and it's really hard to compress all this into one video, so I'm just not going to do it. There's too much good stuff here. We're going to make another video. I mean, Tory Bruno showed us around the top of the MST, and it's just amazing, right? We got to talk technical with the man who's an actual rocket scientist on top of the tower next to his rocket. Please consider subscribing to Smarter Every Day if you don't mind. We're almost home, and we're trying to do it safely. So, I'm Destin. You're getting smarter every day. Have a good one. Bye.